Welcome back. We are going to talk about nuclear magnetic resonance in this lecture, also known as NMR. And before we start talking about the instrument and the spectra itself, I want to discuss the idea of spin and nuclear quantum numbers. As you may recall from general chemistry, an electron possesses a spin quantum number. It could either be rotating clockwise or it could be rotating counterclockwise, and we assign to each one of those rotations a quantum number, plus 1/2 or minus 1/2. The story is actually very similar for the proton. The proton, as well as the electron, they both belong in the fermion family, and so they have the same characteristics in terms of the spin. You could have negative spin or positive spin, specifically half spin, associated with the particle. And this is not exclusive to just the charged particles. The neutron also possesses the same characteristics. All of these particles by themselves are fermions, simply because they have half spin associated with them. Now, the other thing that we're also going to talk about that will be of importance is the fact that when a charged particle spins on its own axis, it does create a magnetic field. And this will play a big role in the NMR spectra that we'll talk about later on. Now, one thing that kind of gets overlooked oftentimes in organic chemistry, but I think it's important to at least show it, is the fact that much like electrons do end up yielding different orbital levels that they populate as you're coming up with electron configurations, the nuclear state also has its own rule of quantum um, levels, and I'm showing it right here. This is basically the different the nuclear orbitals that you populate, and pretty much the way this works is that you do this for the protons on one set, and then on a different set, using the same overall look of the diagram, you apply it to the neutrons as well. So this is the way it works. So let's say you have a regular proton. So this is hydrogen with only one proton. There's no neutrons in there. Well, what will happen is that for your proton, you will just input that electron on the first box of this diagram. And because that's the only thing you have in here, well, that um, occupancy is worth 1/2 spin. All right, but then if we move to the heavier counterpart of hydrogen, so deuterium, all right, deuterium is still only contains one proton, so we still have the one proton upspin electron, on the first box right here. But we also have a neutron, which is the reason why deuterium is heavier than regular hydrogen. And the neutron is gonna be applied to its own quantum diagram. So for the one neutron, we'll have the individual upspin neutron in the first box, and so what we have is now a half spin from the proton box, half spin from the neutron box. If you add those two together, you're going to end up with one spin. So actually deuterium has a full spin as a whole, and that has some other consequences and advantages that we can definitely um, utilize to end up with a pretty clean spectrum at the end. We'll mention that later. You can continue the process, moving on to other nuclei. So if we look at carbon 12, like the most abundant isotope of carbon, you have 6 protons within carbon 12, and you also have 6 neutrons, right? And that gives you the overall mass number of 12. If we populate the boxes, we can only place 2 fermions per box, the same way as it did work for the electrons. So you will place 1, 2, then 3 and 4, 5 and 6, right? And the same thing goes right here. So you end up with no spin for the proton boxes, no spin for the neutron boxes, because they all cancel out. You have, full upspin, downspin boxes in each case. So what ends up happening is that carbon 12 doesn't have a nuclear spin. and because it doesn't have a nuclear spin, it cannot create its own magnetic field, and so we don't really observe an NMR spectrum for carbon-12. However, if we change the picture to carbon-13, which is the other natural isotope of carbon, um, then here we have a different picture, because yes, we still have 6 protons present and they all cancel out in terms of the spin. But if you introduce one more neutron to get to carbon-13, well, now the last neutron is not paired up, and that means that now you have a half spin left over. And overall, what that means is that, well, 0 plus 1 half is equal to 1 half. So carbon-13 is actually NMR active. And when we do take carbon NMR spectra, we do it via carbon-13. Now that creates some problems of its own, because carbon-13 is the least abundant natural isotope of carbon, if you don't count carbon-14, that is. So due to that, you have to have a really concentrated sample to get a good spectrum. You have to basically run the experiment for longer times than you would for, like, an experiment in which you were looking at proton, but we'll get to that later. All right, there's other nuclei as well that do possess nuclear spin that I kind of want to mention so that you're aware of them. One of them is fluorine-19. Now, fluorine is the 9th element in the periodic table, so you have 9 protons. And to come up with a mass number of 19, you have to have 10 neutrons in there. So if we populate the levels, we have 2, 4, 6, 8, and then 9. So this gives you a half spin for the protons. For the neutrons, you have 2, 4, 6, 8, and then because you have the 3 boxes at the same level, you have to populate them one at a time with the same spin. So this gives you an overall whole spin. Now for fluorine, something interesting happens. And I'll be perfectly honest, this type of rules, this is where, I'm definitely not super educated on what's happening, because this is more quantum physics than chemistry. But pretty much what seems to happen is that the whole spin and the half spin of the protons are subtracted from each other, because the end result is that fluorine-19 is actually only worth a half spin altogether. And you can get that from subtracting these things. Now, the reason it's being subtracted, it probably has to do with um, some type of ferromagnetism associated with these nuclear levels. But, that's a little bit beyond my expertise at this point. Now, moving on to phosphorus 31. We have 15 protons and 16 neutrons. If you fill up the boxes to get to 15 protons, you end up with the last box being unpaired, so this will be a spin of 1 half. For the neutrons, however, you have 16, so you actually fully pair up every single neutron, so you have no spin coming from the neutrons altogether. So overall, phosphorus 31 has a half spin, so you expect it to be NMR active, the same way that you would expect fluorine-19, carbon-13, and hydrogen-1 to be all NMR active. So as I said earlier, we're going to see how having a charged particle spinning on its own axis producing a magnetic field is going to affect the relationship, especially when you bring this particle to an external magnetic field, which is the essence of NMR. So let's talk a little bit about the instrument to see how this kind of works out. Now the instruments actually come in all shapes and sizes. Um, the greater the magnetic field that you want to apply, the bigger the instrument. So you can see right here you have a Bruker 900 megahertz instrument, and it's not the instrument that has the highest amount of magnetic field. In fact, the one right here, this Varian one with 1 gigahertz worth of frequency, which correlates to the magnetic field. This one is pretty huge, and you can see you actually have staircases to get to the top to add your sample. Other ones are a little bit smaller, like this 600 megahertz. And then there are some benchtop instruments that make it a little bit more convenient to house the instruments in a laboratory and do the experiments. But you cannot sacrifice a little bit of the precision and spectral detail by using lower magnetic field instruments. Okay, so the way this basically works is that you have your sample placed in between magnets. And so what happens is that the magnets are creating a magnetic field that's passing through the sample. When this takes place, the material, if it has protons, if it has carbon, which will have carbon 13, is going to get magnetized. And pretty much because the spins can either be upspin or downspin, you create two different energy states. The case where you are lining up with the magnetic field of the magnet is the lower energy state, the more stable. But if you do align with spin that's opposite to that of the magnet, well, then you create a situation that is less stable, and this is the higher energy state. So then what happens is that in the presence of that magnetic field, you radiate the sample with radio frequency. And the radio frequency is of just the right energy to account for this energy gap from the lower energy state to the higher energy state. So if you send a range of radio frequencies, one of them is going to match up with this energy change. And when that happens, you will have absorption of radio frequency and the spin of the nucleus will change to the downspin, basically the higher excited state. But once you stop sending that um, light to the sample, well, the excited state no longer has that input of energy. So the only thing it can do is relax back to the ground state, which is the up spin. And when it does that, it will emit energy out from the sample. And then that energy is going to be fully associated to this energy discrepancy from the excited to the ground state, which is received by this coil that wraps around the sample. And the coil basically sends that signal and amplifies it, to the analog, computer system that then reads out your spectrum. So this is how the whole thing works out. And there's more to it, of course, but we're not really going to touch on the itty bitty physics of the process. Now, in the next video, we're going to start talking about how the spectrum tends to look, where the peaks tend to fall based on what functional groups you have, and you'll start seeing that there is a trend, much like we saw in infrared spectroscopy, but this time we're going to add a lot more structural features that will allow us to ultimately figure out the shape of the molecule. Okay, so I will see you in the next video.